Hello and welcome to this quick tutorial on how to convert a tabular dataset to a graph dataset. I think this is the most frequently asked question, and because of that I thought it makes sense to build a simple notebook in which I explain how to convert a simple CSV file into a graph dataset in order to apply GNNs. So this first video is a regular graph dataset, and the second video I'll upload is all about temporal graph datasets, which are a bit more complex. Besides that, I also collect some more frequently asked questions. For example, what if you have pairs of graphs? What if you want to use images as nodes and things like that? These are also questions that many people have asked. Now with that, let's begin with the first section. How do you convert a regular CSV file into a graph dataset? So I've grouped this notebook into 7 steps until you arrive at a graph dataset. Step 0 is to bring some creativity and not lose hope. It can be very challenging to convert a tabular dataset into a graph dataset, but just keep trying and also look at the examples in this notebook. I am sure you will figure out how to do it. Step 1 is then to identify the nodes, the edges, the node features, the labels, and optionally the edge weights or edge features for your dataset. If you have a CSV file with some items, usually these items represent the nodes. This can be people, locations, cars, whatever. And the difficult part is usually to figure out how those are connected. And then you have node features. Those are simply the attributes that describe these items, people, locations. And then you have labels, and there can be 3 types of labels. Either you have labels for the nodes, or you have labels on the edges. So that means you do link prediction, or you have a label for the whole graph. So before starting with the implementation, I recommend to first think about what are your nodes, what are your edges, and all of these attributes. This will give you a better feeling for how your graph will look like in the end. An important design decision is if you have a homogeneous graph or a heterogeneous graph. A homogeneous graph has the same node and edge types. For example, you have cars as nodes and then connections between these cars. And in heterogeneous graphs, you have different node types. For example, users and items. And those different node types typically have different node feature vectors. And because of that, they don't fit into one joint matrix. And instead, you need to separate them. And this can be done in heterogeneous graphs. It's the same for edges. If you have different edge types, you also need to go with the second option here. So I will just roughly go over 2 examples I picked out from the internet. And those are just random data sets I found. Note that I try to keep this video short, and because of that I will not go into detail on all of the code parts, but I've written a lot of comments and text to explain everything. So this first data set is the FIFA 21 rating data set. It's a data set that consists of players, their skills, and their teams. And so I don't know if this data set is suitable for a graph data set, but I just thought I select any data set I find and try to convert it to a graph. As mentioned previously, the first step is always to identify these properties. So what are the nodes here? Those are simply football players, and those are identified with a unique ID. Regarding the edges, we have to come up with a way how to connect the players. I discuss a couple of possibilities down here. And then the node features are simply some attributes about each of the players. For example, you have ball control, dribbling, different features about each of the players. And then there's one feature column or one column called the rating, overall rating. And for example, the task could be a node level regression task, predict the rating for each of the players given some team assignments. The way how I will connect the players here is simply by their team assignment. So if 2 players play in the same team, there will be an edge between these players. And this will eventually lead to one large graph. And because of that, we only have one single graph. And in other data sets, it might be possible that you have multiple graphs or even temporal graphs that change over time. I've also discussed some options here, what you do in case you have multiple graphs. The next step is to extract the node features, and that's usually a very simple step. For each of the items or entities in your dataset, you simply extract the features you have. And here we use things like the ball control, dribbling, so some attributes that describe the entities in your dataset. Typically, you have to apply some one-hot encodings here if you have non-numerical features, and this is also something I did here. One important point is that all your matrices in the end, so you have this node feature matrix now, all of these matrices need to be converted to NumPy in most of the libraries, and you end up with a shape of number of nodes, so those are the football players, times number of features. Here you have 18 features. The next step is to extract the features, and here we have a node level prediction problem because we want to predict the rating for each of these nodes. So you have as many labels as you have nodes. Because of that, our final shape is the same as here, but just one attribute per node. And this is the overall rating. Of course, you can also normalize this here, but this is generally how it's done. Again, we convert it to NumPy, and that's our second matrix. Now, this is the probably most difficult part. You need to connect the nodes somehow. And either you have some relational information in your data set, or you have to come up with some clever way how you can connect the nodes. And as I said before, here I'll just connect them according to their team assignment. But I also mention here that this is not the most sophisticated way to do it. And I wouldn't use a GNN with this graph because it doesn't make a lot of sense. One important point is that you should always start your IDs from 0, because later when you build the edge index based on these IDs, the ID with the number 0 will reference to the first item in your node feature matrix. So here I simply build all of the permutations inside of the teams so that each player inside of one team is connected with all other players. And then the edge index typically has a shape which is called COO format, and that's a representation of the adjacency information, and that has a shape of 2 times number of edges. And those indices here correspond to the IDs in your node feature matrix. So node 0 is connected to node 7. And because of that, it's important to remap your IDs so that they start from 0, so that it's easier to build edges. After that step, you have basically everything you need. And I have some samples here how you can build a data object in PyTorch geometric and put it into a data loader. So we have X, which was the node feature matrix of the football players. We have the edge index that is based on the indices of these football players. And we have the labels Y. And with that, we can build a graph in PyTorch geometric and use it to apply GNNs. So that was the first example in this notebook regarding a node level regression problem on one single graph. And the second one is a heterogeneous data set. And here I simply selected the anime recommender database. So that's a simple recommender system database. So you have some IDs for movies and you have some users, and then you have this rating matrix that tells you this user rated that movie with this score. So again, just like before, we first need to identify the properties of this graph. So we have nodes, and those are, now that's because it's heterogeneous, users and items. We have 2 node types. And then we have edges, which are simply if a user has rated a movie and also how the rating is. Then we have node features, and here we have different features for the users and the movies. So that means we have 2 different node feature matrices. And then we have labels, which are simply the link prediction problems. So we have the ratings between a user-item pair. Again, we have one single graph here. And if you have multiple graphs, have a look at section 1.1. I describe how to proceed with that. So step 4, extract the node features. And we first do it for the anime movies. And just like before, we also re-index the movie IDs so that they start from 0, which makes it easier to build edges later. And here we just use some properties we have in the dataset. We want hot encode the movie type and some other things. And with that, we have a node feature matrix. Just like before, we converted to NumPy, and our node feature matrix has a shape of 12,000. That means we have 12,000 movies times 48, which means we have 48 features. I just realized I forgot to one hot encode the type, but I'll just ignore it. And then we do the same thing for the users. And here the problem is we don't have a user matrix. And if you don't have node features, there are different ways to handle that. Either you insert some dummy vectors like randomly sampled values, or you calculate some statistics about the users based on this rating matrix. Or if you have no information at all, you can also just use the degree or the neighborhood information or even a node-to-vec embedding to represent the nodes in your graph. So in this example, we use some statistics and calculate the mean rating for each user and how many times the user rated. And this allows us to assign some properties to each of the users. So we convert it again, and our second node feature matrix now has a shape of 70,000. That's how many users we have, times 2. After that, we extract the labels, and those are simply the ratings. And here we have a link prediction task. That means we have the labels on the edges. I plotted some distributions of the labels. -1 means that the user has watched a movie but didn't rate it, and this is the distribution of the ratings. Usually I would normalize this to improve the learning later. So in this data set, as I said, I selected a random data set from the internet. Here were also some caveats. So in the rating matrix, there were some movies for which I had no information in the movie database. So I dropped those. And another thing is that you have those movie IDs, but have way less movies in the rating matrix. And that means we only have some labels for some of the pairs. If you think about a matrix, it's that you want to do this matrix completion in a recommender system. I also have a video on that. And the thing is that we only have for some of the cells information, and that's why we need to store, in addition, an index that tells us for which edges we have information, and that turns out to be exactly the edge index. So first, of course, here we have the labels. That's how many ratings we have. And the edge index now has the same shape and tells us which indices, so which user item pairs have ratings. And in order to do that, so that's the important part, your IDs need to start with 0. So if your ID starts with 1, that corresponds to 0 in your node feature matrix. And because of that, it's important to do that remapping so that it looks like this. So that means user 0 is connected to movie 10, and that corresponds to the actual node features in your node feature matrices. And in the end, you have this edge index 2 times the number of edges, and that's exactly how many labels we have. Also note that we have unidirectional edges here. That means we only have an edge from user to this movie, but not from this movie to the user. So if you want to have bidirectional edges, you of course need to also add the other direction here. For heterogeneous data sets, there is a special object type in PyTorch geometric called heterodata, and this data type can hold multiple node feature matrices. For example, one for user, one for movie, and also multiple edge types. Here we have just a single edge type called rating between user and movie. And if you want to learn more about these heterogeneous graphs, there's a great tutorial in PyTorch geometric. Also, if you specifically want to build a recommender system, there's also a tutorial on bipartite graphs. Now, that's all. As I mentioned, please read through the notebook because I can't capture everything in this short video. And this was the first part to build some heterogeneous or homogeneous graph datasets. And the second part is an example for building a temporal graph dataset, which is also a bit more challenging. Thanks for watching. I hope you find this helpful, and let me know if you have any questions or comments. And with that, I wish you a great day.